Hello all. I've got the electronics enclosure 99.9% finished here. I just have a few labels to put on some things and some minor wire management. I've printed a ton of heat shrink tubing and labels for this enclosure build. I've been using an industrial label printer that Epson sent me for this project, and I've been pretty happy with it. I've been using the label editing software that's a free download and works with the label printer. The label editing software allows the text to be manipulated and resized quite a bit beyond what is possible on the label printer by itself. Here I'm using the label editing software to place the text at the extreme top and bottom of the label and also resize it to fit on the 23mm width for the terminal blocks. What I really need here is 6mm tape, but I don't have any, so I'm using 12mm and cutting it in half. So I'm going to put these labels on the terminal blocks here, and to do that I'll use these terminal block markers. We've got 4 terminal blocks here, so I'll take the first 4. And just snap it in place. And repeat for the other side. Here on the front I've got volt and amp meters for each of the axes, X, Y, and Z. On the front panel, you may have seen in another video, I also have an A and B axis that I have not installed in this enclosure yet. They're just there for future expansion. I also got a push-on, push-off switch. And over here I've got an exhaust fan, and on this right-hand side there's a intake fan. So the fans blow in, it goes through the enclosure and exhausts out this side. So let's open it up and take a look inside. Here's the push-on, push-off switch. This is a illuminated switch, so I had to run a neutral wire as well as a power wire to it. The neutral is required for the light bulb. Here I've got the DC power supplies. I may run the X and the Y at 36 volts. And the Z at 48 because the Z motor is a larger one. The 48 volts comes out through this connector here and up into this board. The amp and voltmeters up at the top can read up to 100 volts, but they cannot be run on anything higher than 35 volts. And since I have 48 volts coming out of the power supplies, I could not run the volt amp meters on the 48 volts. Which is why I made this circuit board here with a bunch of connectors and a DC to DC converter. It takes 48 volts from the X-axis, drops it down to 12 volts, and then the 12 volts goes out on the yellow and red wires here and powers each one of these meters with 12 volts. And each meter will read out the amps and the volts from each one of the power supplies. Once the power flows through the volt and the amp meters, it comes out through this connector here and down to the stepper motor controllers. One of my design goals here was to be able to remove the backplane so that I could take it out of the enclosure and perform maintenance or change parts or whatever needed being done. And in order to do that, I put Amphenol connectors on several of the cables. This allows things to be unplugged and separated from the enclosure. To demonstrate how this works, I'll remove the power supplies here first. The 48 volts out to the stepper motor controllers disconnects here. And down underneath here, I have an Amphenol connector for the 120 volt mains to feed the power supplies. With those two disconnected, the hinge pins can be removed and the power supplies just come out. I've got the 120 volts coming in here, and the 48 volts comes off from each one of the power supplies underneath and is held in place with these zip tie anchors. I've got several other connectors here that facilitate removing the backplane. This is a 9-pin connector, which is the 120 volts coming in from the 3 power connectors on the front. I also have a connector here for the e-stop switch. And all these connectors are keyed so they can only plug in one way. I also have a connector here for the start-stop switch. These are the 48 volt lines into the stepper motor drivers. We'll just disconnect these right from the stepper motor drivers. I don't know if you can see, I 3D printed little keys that come over and make a 90-degree turn. And I put those on these power connectors here so that the power connectors are keyed. The stepper online, they use the same connector for the encoder as they do for the power. So if these are disconnected without the key, it might be possible to plug the power line into the stepper, into the encoder connector. And that would be very bad, having 48 volts feeding into the encoder. So I keyed them so that this cannot be plugged in, because the key hits on the connector next to it and it won't plug in. But if I put it over here, it bypasses the connector and it allows it to be plugged in. Just a little bit of security, safety there, so that I don't accidentally plug the connectors into the wrong place. So we'll disconnect the power and the encoder from each one of these. I didn't put a key on this lower connector because it is much larger than the other ones. There's only one place it can go. And I've got the fan connectors here. The fan connector on the other side. Ethernet cable. These are the encoder cables. And if I didn't miss anything, this backplane should just lift right out. And here I have the backplane out. This makes it easier to work on, easier to change parts. I can flip it over and get to the screws on the back side of it if I need to change anything out. Now that I've got the backplane out here, I'll do some of the minor maintenance I need to do. I have to put covers on some of these wire duct that don't have wires running through them when I put the backplane in and take it out. I don't have any wires running through this bottom one, so I'll put a cover on that. I also need to feed these wires out where they belong and put a cover on this back one. The rest of the wire ducts have wires that need to run in them when I reinstall the backplane into the enclosure, so I won't be able to put the covers back on until it's installed. This particular wire duct is going to be a bit of a problem because of the power lines that come into the various stepper drivers here. There are so many wires in this small area that I won't be able to get a cover on it very well. So for this one, I think what I'll do is put a small section of cover here, and then this will be all covered over with wires anyway, and you still won't be able to see it. Here's the self-centering mount for the DB25 connector. This moves around and it finds its home in that front panel. Before I put the backplane back into the enclosure, I'll talk a little bit about the various sections. When I first started the project, my plan was to use a 24-volt DC coil in the contactor. I was having difficulty finding a contactor with a 24-volt DC coil even in stock, so I ordered the 120-volt coil instead. This meant for controlling the 120-volt AC coil in the contactor, I was running 24 volts into one of the accessory relays, and the accessory relay would then switch the 120 volts to activate the coil in the contactor. So the end result is a relay switching a contactor. A basic overview here. This area here is the 120 volt mains that comes in. 120 volt comes into this circuit breaker, and then it distributes out to this set of terminal blocks here, which is unswitched 120 volts. There's a couple of fuses in here for the two switched outlets on the front of the panel. And then this is a switched 120 volts that is one of the outputs of the contactor. And then on the end here is a neutral block for distributing the 120 volt neutral side. Next up is the 24 volt DC section, as well as the accessory relays. The accessory relays, I've got a couple of layers here. I've got two of them that are used on the bottom and three of them that are used on top. The DC power supply I'm using is a Meanwell 24 volt 1 amp. I went with a 1 amp power supply because I don't anticipate needing much more current than that. My limit switches are proximity switches. I have 9 of them, However, they're only about 10 milliamps each, so 9 of them is only 90 milliamps, or less than 10% of the capacity of this power supply. These relays over here are also about 10 milliamps, and I'm running up to 8 of those is another 80 milliamps. So with the 2 of those, we're what, at 170 milliamps, still less than a quarter of the power supply needs. I also have 24 volts running over here to the Mesa card, and its power needs are also very small, about 100 milliamps for the card, and then it's the field outputs that are the primary consumers of energy in the whole circuit. But currently the only outputs I'm using are for the relays, so they're only 10 milliamps each. The stepper motor drivers are more or less self-explanatory. They get the 48 volts in from the power supplies. The encoder inputs come from the front panel, and the alarm and the step and direction are permanently wired to the Mesa card here. I've got a set of terminal blocks here. These are primarily for the alarm output on the stepper drivers. The stepper drivers output a negative signal, and the Mesa card likes to see a positive signal. So what I had to do is add pull-up resistors, one for each one of the alarm outputs. The pull-up resistors will pull the inputs up to 24 volts, and in the software you set it up telling CNC that when it sees 24 volts everything is normal. When an alarm is triggered by one of the stepper drivers, it outputs a ground, overrides the 24 volts from the pull-up resistor, and allows the input to drop to 0. And when an alarm input drops from 24 volts to 0, it signals to LinuxCNC that there has been an alarm activated. The next section up here is the 24 volt DC distribution. I have the negative side and the positive side. The positive comes out and runs through a bunch of fuse holders. The fuse 24 volts out then goes and feeds various parts of the system. The Mesa controller card has the outputs for the step and direction for each one of the stepper drivers. It also has outputs over here for the accessory relays, inputs for the alarms from the stepper drivers, and these are all the inputs from the homing and limit switches that I'll be setting up out on the CNC mill. The homing and limit switches will be hooked up to a DB25 connector at the mill and fed into this DB25 connector. Pins 1 and 2 are the negative side of the 24 volts. 3 and 4 are left empty just for isolation, and 5 and 6 are the plus 24 volts. So my limit and homing switches start at pin 7 and go up from there. So when I wired them up, I started with pin 7 input on the Mesa card. So 7 here matches with 7 there, 8, 8, 9, 9, and so on. That just keeps the wiring more intuitive. Here's a ground distribution block. It provides the chassis ground for the system. There's chassis ground here on the Mesa card, chassis ground here on the DC power supply, and also chassis ground or shielded cable ground here for the DB25 connector, as well as chassis ground and earth ground for other parts of the system. And here's a additional terminal block for negative side of the DC 24 volt power supply. The last thing I'll look at here is the e-stop switch circuit. The e-stop switch is wired through the normally closed side and allows power to flow through the coil in the contactor. When the e-stop switch is pressed, it opens the circuit and therefore opens the contactor. When the contactor is deactivated by the e-stop switch, it shuts off the 120 volts to the power supplies that power the stepper motor drivers, and it also shuts off the 120 volts that goes out to the accessory outlets. The 24 volt DC power supply is wired through the unswitched terminal block here, and that stays active when the e-stop switch is pressed. This allows power to continue to the Mesa controller card so that LinuxCNC can be told that there's been an emergency shutdown. The 120 volt relay here has 24 volts coming in the common, and the normally closed side is connected to the Mesa controller card. When the system is running normally, this 120 volt relay is energized, and the normally closed contact then becomes open. When the e-stop switch is pressed, the 120 volt relay is de-energized, and 24 volts is fed out through the normally closed contact to the input of the Mesa controller card, which instructs LinuxCNC that the e-stop switch has been pressed. LinuxCNC will then tell the stepper motor drivers to stop all movement, so that even if the e-stop switch is reset, the mill will not continue moving. So the next thing to do is to put this back in the enclosure. This backplane is mounted into the enclosure with 4 screws in the corners, and they're a little bit inaccessible. So what I've got here is a screw starter. I don't know if you've ever seen or used one of these before. This screw starter can be pretty handy for Phillips head screws, and there's also a side for slotted screws. But you prep it, you sort of cock it, twist it, and pull it out, and then it goes into the screw, give it a push, and a little blade in there locks catty corner into the screw, and it holds it exceptionally well. Then you can just run the screw in to get started. I've had this for probably 20 years. This one is stamped with the name Ullman Devices, U-L-L-M-A-N Devices. Then once they're all started, just go back in with a regular screwdriver and tighten them down. Now I'll just reconnect all the connectors, put on the wire duct covers, and reinstall the power supplies. And power. Well, I'm seeing an error here. I've got no power to the power supplies. However, the exhaust fans are running, and I do have 24 volts. And the reason for that is I forgot to plug in the e-stop cable and the e-stop switch. Since the contactor gets its energy for the coil through the e-stop switch, the contactor will not activate without the e-stop switch connected. So let's try this again. There we go. 36 volts, 38 volts, 34 volts. Each one pulling about 50 milliamps, 40 milliamps, 60 milliamps. 34, 39, 36. Yeah, they're pretty close. I laid the cover on the e-stop switch, and it temporarily disconnected the contactor. So let's take a look. This is our e-stop relay, which is energized when the contactor is energized. I have an alarm flashing here on the Z. For some reason, this particular stepper motor driver alarms when there's no encoder connected. These two do not alarm when there's no encoder connected, so they're just similar but different. I'm assuming that when I connect the motor to this, that the alarm will not activate. So now let's press the e-stop switch. This light should go out and the contactor should disengage. Correct. When this light goes out, it sends 24 volts over to the Mesa card, and that will tell LinuxCNC that the e-stop switch has been depressed. Reset the switch. Re-engages the contactor. Everything operating as it should. It takes several seconds for the capacitors to drain, but I suspect it will be much faster once the motors are connected, because the motors will put a load on the stepper motor drivers. Excellent. Next step is to connect it up to the mill and see if we can get some motion out of the axis.